Hey guys.
What up?
Not much. How are you?
Doing all right. Just waiting for class to start.
Sounds good.
Oh, Professor, are you on campus?
Yep. I'm in my office right now.
Oh, okay.
Yeah, I have in person. So last week I was a little bit sick, and so I stayed home. But this week I'm feeling better, so I'm here on campus.
Professor,
Yep.
I have an off-topic question for you.
Sure.
I think last time we were showing us your YouTube channel,
Yep.
I think you were subscribed to Gaijin Hunter.
Yeah.
Oh, does that mean you play Monster Hunter?
I do, or I did, I should say. So I
Or you-
played a lot when World was out, but I haven't picked up the newest one yet, which is Monster Hunter Rise. But
Right.
yeah,
I was just curious what weapon you used.
Oh, I use the I like to use the lance a lot.
Oh yeah, that was pretty good in World. Yeah.
How about you?
Oh, I'm a hammer guy.
Nice.
Unfortunately, I'm the minority.
Oh, really? I feel like hammer is decently popular. I mean, not as much as longsword, but it's
No, longsword's always first, which they always trip you, of course.
Yeah.
I think there was there were some statistics for this month, and of course, longsword was first again, but lance was unfortunately last.
Yeah. It usually is. It's not a play style that people enjoy a lot, but
yeah, just poking all day.
Yeah. Hammer's usually middle of the pack. I feel like though, like usually like anywhere between like 5 and 10 of the weapons.
I would expect so, yeah, but turns out not too much.
Hey, Professor Tran,
What's
our
up?
410 class today is in person, right?
Yep, yeah, but I'm also going to stream it on Zoom as well. And
Oh,
so,
okay. Because I got my second dosage of the vaccine, so I'm actually running a fever right
okay.
now. And I think just going to school would just not be the smartest idea when you actually actively have a bit of a fever. So
Yeah, no, I agree. Yeah, it's, and other people have said too that, they're in situations where it's hard for them to come to school, but they still want to take the class. And so yesterday I tried it out. And so what I did was I basically have this set up with my laptop and my iPad, and I brought it into the classroom. And so I was in person with the people that are there, while also, streaming it virtually as well for the people who want to stay home. And so it seemed like it worked pretty well. And so I didn't get any complaints, and people said the audio was still fine. So and so
Okay, cool.
I plan on keeping that up for the rest of the semester. And so you can choose to kind of come in or, stay home if you want. Okay, it's 1 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today?
Pretty good, just a little tired.
Good, good. That's good. Yeah, second week of school, so everyone survived the first week, and so that's always a good thing. Okay. So as you guys can see, I'm not in my home anymore. I'm in my office. So last week I was feeling a little bit sick, and so I was actually staying home for that. But actually, in reality, you know, I do have some classes in person this semester, and so you know you'll probably see me here a lot more often than you will at home. So hopefully the audio here is a little bit better because I'm in this enclosed space instead of in my apartment. And there's no cat, you know, to kind of bother us. And I know in my home I have that like lamp that's like kind of really blinding in the back right here, and so obviously you don't see that anymore. So that's a little bit better. Yeah. Yes, I have a cat. She's old. She's like she's 16 and a half years old. But sometimes she'll meow during the class, and it's a little bit annoying. But yeah, but she hasn't done it recently. But here, you know, we don't have to worry about that. Okay, and so this is lecture 3, and so we're at the beginning of the second week, and so the plan for today is we're going to pick up where we left off on last Thursday when we were talking about the time value of money. Okay, and so we're going to continue on with lecture note 01. If you're following along in the lecture notes, I'm starting on page 9, and then you know we're going to get as far as we can for today. Okay. Another announcement. So I did post a homework, and so I noticed that some people have already started on it because I've gotten some questions over the weekend, and that's going to be due next Tuesday. Okay, and so I think for a lot of that assignment, you probably don't have the tools to do any of it yet, except for maybe the cash flow diagram problem. But problems 3 and 4, you know, we're going to go over how to do those, you know, today, or we'll cover the knowledge that you need for that today and on Thursday. Okay. Okay, so are there any questions that I can answer before we get started? Okay, all right, so let's go ahead and get started. Okay. And so last week, you know, I think I left you guys with kind of a theoretical situation, right? And so it was kind of the scenario of the $100, right? And so I asked you guys, you know, if I have this $100 bill in my hand, I don't actually have one right now. Would you rather have that money? Would you rather get that money right now, or would you rather get that $100 sometime in the future, right? And pretty much everyone said that, you know, you'd rather get the $100 now because then, you know, that $100 will actually have value to you, right? You can take that $100, you can spend it on something, you can buy, you know, maybe a really nice dinner, or maybe, you know, a new part for a hobby that you have, right? But most importantly, you know, what you can do with any money that you have now, you can invest it and then have that money grow, you know, to a bigger amount sometime in the future. Okay. Okay. And so for this reason, and also the reason that, you know, any money that you have now, you can spend it on something. Money that you have now will always be more valuable than money you'll have in the future. Okay. Okay. All right. And so now that we've kind of established that, you know, now the question is, you know, how do we quantify this growth, right? And so, you know, in this definition that I have here, or this statement, you know, I have this kind of generic statement here called grow. Okay. And so the question is, you know, how much will money grow over time if you do invest it, and how do we actually quantify that? And the way that we do that is through interest rates. Okay. And so the next kind of you know, chunk of the notes is going to be based on interest. Okay. And so interest, you know, is a very centrally important topic to any kind of economics that you do. Okay. And so it's going to be, you know, really important for the things that we do. And of course, you know, for engineering economics, you know, for companies, you know, they're always thinking about what kind of interest rate that they can get. Okay, right. And so the definition of interest rate, it's a percentage. It's a percentage number that expresses how much a certain amount of money will grow in a certain period of time. Okay. Okay. All right, and so you've probably seen, you know, you've probably seen billboards, you've probably seen advertisements for, you know, companies that are giving out home loans and they have a certain interest rate, right? And they always like to advertise how low their interest rates are. Okay. Okay. And so one, I think probably the most you know, the most applicable or the most common way that you come in contact with interest rates is through loans. Okay. And the whole concept of a loan kind of is you know, it encapsulates kind of the statements that we have at the top of this page, right? And so the reason people take out loans is that, you know, they want to have more money right now, right, in order to buy something or purchase something new. Okay, so a lot of times something like a big purchase, like a house or a car, or for engineering purposes, you know, a lot of times companies have to take out loans to purchase a piece of equipment. Okay. Okay. Right. But in order for this to be worth it for the lender, right? And so if someone lends you money, whether it be a bank or whether it be, you know, your friend or someone, right? There has to be something in it for them, right? And so, you know, when you pay back a loan, you know, I think everyone knows that you don't just pay back the principal, right? And so if you borrow $100 from someone, you know, you don't just pay him $100, right? So maybe a month later, a week later, you pay him back $100 plus interest, right? And that interest is kind of an expression for how much that money grew while you were borrowing it. Okay. And so I think probably the easiest way to kind of express this is with an example. And so I'll do that on the next page. But before we get into the example, are there any questions on this? Okay. All right. So let's do an example just to kind of illustrate, just so that you can kind of see the math in action. Okay. All right. And so let's say that you have a friend, okay, and your friend wants to borrow $5,000 from you. Okay. And he says he's going to use that $5,000 to start a business. Okay. And what he says is that, you know, this what he anticipates is that, you know, after 5 years, then his business is going to be profitable and he'll be able to pay you back. Okay. Okay. And of course, since you're lending him a very large amount of money for 5 years, you don't just want $5,000 back, right? You also want to collect some interest. Okay. And so what you two agree to is that, you'll say you'll lend him the $5,000, but you're also going to charge him 8% interest per year. Okay. And in fact, for this problem, we'll say it's 8% simple interest per year. Okay. And so for this problem, we want to compute two things. Okay. And so first we want to compute how much interest are you going to earn after the 5 years. Okay. And the second thing we can compute is how much total is your friend going to pay you back after the 5 years. Okay. All right. And so let's give some terminology to these numbers, okay? Just so that we can kind of refer to kind of the same things going forward, right? And so first, let's consider the original $5,000 that you're lending your friend. Okay. And so the original $5,000, oftentimes we call this either the principal of the loan, right? Because it's the original amount that's being lent out, okay? Or a term that we'll use a lot in this class is that we'll call this the present sum or the present worth of the money. Okay? Okay. And so that $5,000 that you're lending out is $5,000 worth of stuff, that you're lending out right now. Okay. All right. And so now let's compute the amount of interest that we're going to earn. Okay. Okay. And so what your friend says is that he's going to pay you 8% simple interest per year. Okay. And so what that means is that you're going to compute 8% of the original principal. Okay. And so the principal here is $5,000. Okay. Okay, so we take $5,000 and we just simply multiply it by 8%. Okay. Don't multiply by 8. So we want to make sure we multiply by the fraction. Okay. And so if we take $5,000 multiplied by 0.08, okay, and what this is going to give us is $400. Right. And so each year, we're going to earn $500 worth of interest. Okay. Okay. And so if we're earning $400 each year, all we have to do is just multiply this by 5 years, and that'll give us the total amount of interest that we're going to earn over this loan. Okay, and so we take $400 multiplied by 5 years. Okay. and this is going to give us $2,000. Okay. And so, over the course of the 5 years that you're lending this money out, you're going to earn $2,000 on your investment. Okay. All right. Any questions on this example so far? Okay. All right. And so now that we've computed the total amount of interest, all we have to do is just add this together with the principal, and that's going to be, the amount of money our friend is going to pay us after 5 years. Okay. And so remember, our principal was $5,000 plus $2,000 interest. Okay. And so we add those up together, then we get a total payment of $7,000. Okay. And so after 5 years, your friend, if he didn't take your money and just bounced, he's going to write you a check for $7,000. Okay. All right. And so this was an example with just simple interest. Okay. And so simple interest is fairly simple, right? And so the way that you compute simple interest is, using this simple formula here. Okay. And so we kind of did it in 2 steps, but you can kind of do it in one. Okay. Okay. And so the simple interest formula is given by P, which is the principal or the initial sum, present sum. Okay. You're going to multiply by I, which is the interest rate, and then you're going to multiply by N, which is the number of periods. Okay. All right. Remember, the important thing is whenever you're plugging in for the interest rate is to always use a decimal and not a percentage. Okay. All right. And so the important thing to remember with simple interest is that the reason it's called simple. Okay. The reason it's called simple is that, when you compute the interest payments, you only apply it to the principal. Okay. Okay. And so, even though, if we take this past example, right, even though you're making $400 each year, right, that $400 that you're making each year doesn't get folded into the principal, right? And so you're only collecting interest on the initial money that you lended out, not any of the interest payments. Okay. Okay. And so that makes calculations really easy, right? And so you only have to remember just what the initial principal was, and then all the interest payments are based off of that. Okay. And so simple interest problems, are pretty straightforward, but I will say that they're very uncommon, right? And so what's more common in, out in the real world are compound interest situations. Okay? And so compound interest, the way this works is that, anytime that you make some money from the interest rate, right? And so let's say that, after 1 year, you made $400 from the interest rate, okay? And so that $400 then gets folded into your principal. And then that means that your interest payments for the next year are going to be even higher, okay? And so compound interest, the way that this works is that, you take the interest from the previous period. Okay. The interest from the previous period gets added to any amount that's unpaid, or gets, in other words, gets added to the principal. Okay. Right. And so if the interest payments are being added to the principal, that means, the interest payments for the next period will be even higher. Okay. Okay. And so, what we're going to do is I'm going to redo the example from, that we did previously, but we're going to use compound interest. And what you'll see is that the amount that your friend pays you back at the end is going to be higher than the $7,000 that we have, because each year the interest that we're earning will get added to the principal. And so when we compute the interest for that year, this P here will be higher. Okay. And so if P is higher, that means our interest is going to be higher for that year as well. Okay. All right. Any questions on this before I illustrate it with an example?
Do we assume the interest to be constant?
Yes, that's a good question. So for most of the problems, we're going to assume the interest rates are going to be constant. Yeah. Mhm.
Okay, thank you.
Yep, that's usually the case too. So usually when you take out a loan, the interest rate kind of locks at that time, and so they're not going to change the interest rate on you halfway through. Yeah, if they could, it would cause a lot of chaos, at least for home buyers and things like that. And and those loans will last you about 15, 30 years, depending on the terms of the loan. Yeah. Okay, so let's redo the previous example, but now let's do compound interest. Okay. And so just to sum things up, let me give you the stats for the problem. Okay. Right. So the principal, remember, this is going to be $5,000. Okay. And we'll call this the initial principal. So the principal at the beginning. Okay. Okay. And so the interest rate, which is going to be a compound interest rate now, this is going to be 8%. Okay. And it's going to be compounded each year. Right. And then the number of periods that we have, or the length of the term, is going to be 5 years. All right. Okay. And so with this, I find it a little bit easier to organize it into a table, just so that you kind of see what's going on. Okay. And so let's go ahead and make a table. Okay. And so for the first column of the table, I'm going to put year. Okay. Right. And we'll label this down all the way down to 5. Okay. Next, let's make a column for the starting principal. Okay. Okay. Then let's make a column for how much interest we're going to be paid that year. Okay. Okay. And in the last column, what we're going to do is we're going to take the interest that we earned that year, and we're going to add that to our principal for for the next year. Okay. And so that last column is called new principal. Okay, and so let's start with year one. And so in year one, we're going to start with a $5,000. Okay. Okay, so the $5,000 is the amount that you loan your friend. Okay. And in the first year, we're going to take 8% of that, and that's going to be the interest payments for that year. Okay. Okay. And so we're going to take $5,000. Let me make it a bit smaller just so I can fit it. And then we're going to multiply this by 0.08. Okay. Right. And so just like before, our interest payments for the first year is going to be $400. Okay. It's just going to be 8% of 5,000. Okay. And then the new thing that we're going to do here is we're going to take that $400. We're going to add it to the 5,000. Okay. Okay. And so this is going to give us a new principal of $5,400. Okay. Right. And so then starting on the second year, we're going to take that $5,400, and that's going to be the new principal for this year. Okay. And so we're going to start with the principal of $5,400 for year two. Okay. Right. And so now the interest payments for year two are going to be higher because we're taking 8% of 5,400 instead of 8% of 5,000. Okay. And so we're going to do 5,400 multiplied by 8%. Okay. And so this is going to give us an interest payment of $432. Right. And so you can see now that the interest payment went up because all our principal also went. Okay. All right. And then from there, we can compute our new principal. And so our new principal is going to be the principal at the beginning of the year, which is $5,400, okay, plus the interest that we made that year, which is $432. And it's going to give us a new principal amount of $5,832. Okay. Which we can then move over to the next row. Okay. And then we can just repeat the whole process. Okay. And so for the interest rate, we're going to take 5,832. This is for year three. Okay. Multiply by 0.08. Okay. And this is going to be 467. And so the new principal after year three is going to be 5,832 plus 467. Okay. And this is going to be 6,299. Okay. And then that 6,299 is going to move on to the next line, okay, which we're going to use to compute the interest rate for year four. Okay. And so the interest payments for year four is going to be $62.99 times 0.08. Okay. And so this is going to be 504. All right. And so if we add that together to our previous principal, we get 6,299 plus 504. And it's going to give us 6,803. Okay. Right, and then we can fill in the last line, and that's going to complete our calculations. And so the interest payments for the last year is going to be 544. Okay. And so if we add that together, then we end up with a final principal, or the final amount owed is going to be 7,347. And so if you compare this to the result of the previous one with a simple interest, we can see here that we're making $347 more than we would before, simply by changing to compound interest. Okay. Okay, so there's a question in the chat. And so the question is, will you always want us to round to whole numbers? I would at least want you to round to the whole cents. And so, rounding to the whole cents, I think, probably makes the most sense. But, I'm not that super strict on the numbers too. And so, inevitably, with these kind of classes, which are, or these kind of calculations, which is, it's going to be dependent on, your calculator and where you round stuff off. You're going to be off by maybe about $1 or $2 or $10. And so for a lot of cases, it doesn't make that big a difference. And so I'm not too big a stickler on the numbers. Yeah, for this problem, I rounded to the nearest whole dollar, but you'll see me later on. I'll round to the nearest cent or things like that too. So I'm not too strict about it. Just because it's, in reality, if you're budgeting for like a multi-million-dollar, engineering project, whether you're off by $5 or $6 is usually not that big a deal. Yeah. Okay. Any questions? So any questions on this example? Okay. All right. And so you can see that, with compound interest and, with compound interest, what you're doing is you're taking the interest payments per year and then adding that to your principal, right? And this results in higher interest payments at the end. And so, compound interest is, I think the only I can't even think of a case where you would see simple interest. Simple interest is kind of more just an educational tool. And so, compound interest is the one that you'll really see, out there in the real world, whether you're taking out a loan for personal use or you're taking out a loan for a company, or if you're the company that's lending people money. And so, compound interest is the way to go. Okay. And, a practical thing for this is that, if your family is anything like mine, where, people are always kind of borrowing money from each other, now you can charge compound interest for your loans. And so, you're going to end up with a few more extra dollars in your pocket too. So that's always a good thing, right? And so, next time your uncle asks you to borrow $20, to play poker, you can charge them compound interest and you'll make, just a little bit more money. And that's always a little bit more satisfying in the end, right? Okay. And so that's interest rates. Okay. And so now the next thing that we're going to cover is the concept of equivalence. Right? They already don't pay back without interest. Yeah, that's true. Yeah, if you if you're lending money to your uncles or something, then they just play the uncle card and they just say they've forgotten something like that. So I've been the victim of that as well. Yeah. Okay. All right. Oh no, yeah. Yeah, families can usually families and money usually don't mix that well together, and so you have to be a little bit careful with with that. Yeah. Okay, so let's talk about equivalence. Okay, and so if we think back to the previous problem, right, we had two values of money that we're looking at two different points in time. Okay, right, and so if we compared the $5,000, right, and so that $5,000 is that's money that you have today, right? Okay, and then through the action of the loan, right? And so by loaning that $5,000 to your friend, okay, what we saw was that $5,000 is going to grow to $7,347, okay? Okay, that money's going to grow to 7,347. But that's not going to be valid for 5 years. Okay, and so what we have here is two different amounts of money at two different points of time. Okay, but because they've been related to each other by the interest rate, what we can say is that these two amounts of money are equivalent. Okay. Okay. These are equivalent amounts of money, okay? Given the interest rate and given the amount of time that passes in between them, okay? Okay. And so we're going to be talking about equivalence a lot in this class, right? Oh yes, those are dashes. Yeah, they're not minus signs. Mhm. Yeah. All right. And so, you know, if we kind of write a more formal definition for equivalence, what we can say is that in order to declare that two amounts of money are the same, okay. Okay. In order to say that two amounts of money are equivalent, we need to take into account what the interest rate was and you know how much time is separated in between. Okay. Okay. And the reason we have to take interest rates and time into account is that these factors are going to change the value of your money. Okay. Okay. Right. And so, you know, as an example, you know, if you took that $5,000, but you didn't lend it to your friend, right? But instead you just put it in your pocket, right? And kept it for 5 years, right? So that $5,000 in the future is actually not worth as much as $5,000 today, right? It's the same problem that I gave you before, where, you know, the $100 I give to you in the future, it's not going to be as valuable to you then, because, you know, you're waiting all this time, but the money itself isn't growing. Okay. And so, you know, when we talk about, you know, equivalence of money at different times, you know, we have to take, you know, the interest rate into account. Okay. All right. Any questions on this so far? Okay. All right. And so, you know, given this information about equivalence, you know, it'd be really useful to have a formula to allow us to compute any future sums, you know, very easily. Okay. I should say equivalent future sums. Okay. Because the way we did it in the previous example is we wrote that table, right? Which is fine. You know, I think the table is nice. In fact, you know, it kind of illustrates what's happening at every time point really easily, right? But when you're doing a lot of these calculations, which is you know, which is pretty common, writing a table for each and every single one can be kind of a little bit tedious, a little bit annoying. Okay. But thankfully, there is a formula that we can use, a fairly simple formula, to convert in between, an equivalent future sum given a present amount of money. Okay. Right. And so this formula is the following, right? And so we say that F, okay, capital F, is equal to P times 1 plus I, which is the interest rate, raised to the n power. Okay. All right, and so the way to read this formula is to go. Let's start with P. Okay, and so P here is this is our present sum of money. So this is an amount of money that we have right now. Okay. Right. This I right here is the interest rate. Okay. Again, remember when you plug in for the interest rate, it should be a decimal. Okay. And then this n up here, n is the number of time periods that's going to pass. Okay. Right. And so given all of that information, and this one right here is just one. Okay. It's just the number one. And so there's nothing special about that. Okay. And so if you're given all that information, what you can do is you can compute how much that present sum will be worth in the future. Okay. So this F right here is the equivalent future sum. Okay. Right, and so it's a fairly simple formula here, and this assumes compound interest. Okay, and so actually from here on out for the rest of the class, you can assume that we're talking about compound interest. Okay, and so if we apply this formula to the previous example, okay, we say that F is equal to the present sum. Okay, and so the present sum was $5,000, and so that's the amount of money that we're paying out to our friend right now. Okay. And we multiply this by 1 plus the compound interest rate, which is 0.08, okay? Raised to the 5th power, because we're doing this over 5 years, okay? And if you punch this into your calculator, what you'll get is $7,347. Okay? And so you can see this is a much easier way to compute, compound interest amounts, much more than using a table, okay? Okay. And so this formula will help you compute, compound interest amounts, a lot more easily. Okay. And the way I want you guys to think about this, and and this is not the only formula that I'm going to introduce to you, this week. Okay. And so the way I want you guys to think about this is that, this formula here represents a conversion. Okay. And what you're converting between is you're converting between an amount of money that you have today to an amount of money that you would have in the future. Okay. Okay. It's almost as if you're converting, money from one type of currency to another, right? So you're converting between, maybe US dollars versus, pounds in the UK, right? And so this is you can almost think of this as the same way, right? Where you're converting money that you have in the present, and you want to see how much that money will be worth in the future, given the interest rate that you have and the amount of periods, okay? And if you think of it like a conversion, I think it'll make a lot of the economics part of the class really a lot easier, because we're gonna introduce different forms of cash flow, right? So right now we just have I call these kind of the single payment cash flows, right? So we have a single lump sum in the present, and a single lump sum in the future, right? But once we start getting into things like a uniform series of payments, or maybe a payment that grows with time, like an arithmetic gradient, thinking of these as conversions will make your life, a lot more easy. Okay. Okay. So any questions on this so far? Okay. All right. And so this is the I think the official name that I gave this is the compound interest formula. Okay. We can manipulate this formula to solve for P, right? Because right now the way we have this formula, we're solving for F, right? And so we just plug everything in on the right hand side, and we can solve for a future sum. Okay. But sometimes you want to do the reverse, right? So sometimes you want to compute P instead. Right, and so we can take that same formula and we can manipulate it in order to solve for P. Okay. Okay, and so we say that P is equal to, we're just going to divide both sides by 1 plus I to the n. Okay, P is going to be equal to F divided by 1 plus I raised to the n power. Okay. All right, and so with this formula, what you can do is you can take an amount of money that you expect to have in the future, and then compute how much that would be worth in the present, given the interest rate and the number of periods. Okay? So let's do an example of showing this this formula in action. Okay, and so let's say that you have a situation where you want to have $1,000 in your savings account after 5 years. Okay. Right, and so this is pretty common, right? And so one common application of this, and I think I have a homework problem for this later on in the semester. Whereas let's say that you just had a child, right, and you want to save money for their college education, right? And so by the time your child reaches 18 years old, or by the time they graduate high school, you want to have X amount in their college account so that it will cover their tuition, right? And so you want to determine, if your goal is to have X amount of money in your account after a such amount of time, how much money should you put into your account at the beginning? Okay, and so in this example, we're working with a little bit smaller numbers, right? And so we're for this example, you just want to have $1,000 in your savings account, okay, after 5 years. And let's say that the annual interest rate for your savings account is 2%. Okay, which is really good for a savings account, but I digress. Okay. And so this question wants to know is that if you want to have $1,000 in your account after 5 years, how much money should you put into it now? Okay. Right, and so what we have here is $1,000. Okay. Okay. And so this this $1,000 here is an amount that you want to have in the future. Okay. And so we'll label this as F. Okay. We also have the interest rate here. So the interest rate here is 2%. Okay. And then we also have the amount of time here, which is 5 years. Okay. And so let's take all this information and plug it into the formula that we have here at the top of the page. Okay. And so what we can say is that P is equal to $1,000 divided by 1 plus I. Remember to put the interest rate as a decimal, okay? I know I'm saying the decimal thing over and over again, but every year, there's at least a couple of students that, that get absurd amounts of money because they put in a whole number for their interest rate. So I know it's getting annoying, but I have to keep saying it so that it kind of gets drilled into your head. Okay. All right, and so all we have to do is just punch this into our calculators, and what we get is $905.73. Okay. Right, and so if you have a savings account with with a 2% interest rate, if you put in $905, right now, and you just let that money sit for 5 years, then you're going to end up with $1,000, at the end of it. Okay. And that's money that you didn't have to do anything for, right? You just took that money, you invested it, you didn't touch it, and then it just kind of grew just by itself, right? And so you can see the value of your $905 increased by about $94.27, okay, just by you investing it and just not touching it. Okay, so any questions on this?
Yeah, Professor.
Yeah.
Would this be considered a conversion too?
Yes. Yep. Yeah. Anytime you're considering, cash flow at one time versus cash flow at another time, you can consider that a conversion in between, right? And so that $1,000 in the future, if you convert that to, an equivalent sum in the present, that equivalence or that conversion, it gets converted to $905.73. Yeah. Okay. All right, and so I'm going to skip around in my notes a little bit. So I know I have a section there on nominal and effective interest rates, but that's not really going to be important for the rest of this class. And so for just kind of in the interest of time, I'm going to skip to uniform series. Okay. Okay. And so uniform series is the next kind of form of cash flow that we're going to learn. All right. Okay. And so, so far we've gone over two different forms of cash flow. Okay. Okay. And so the first kind is a present sum. Okay. And we gave it the symbol P. Okay. And then the other type of cash flow that we've gone over is a future sum. Okay. And then we call this F, right? And so like I mentioned before, these two cash flows here, I like to call them the single payment or the lump sum type of cash flows. Okay. Because they they just represent a single amount of money. Okay. But a lot of times you don't often pay back a loan in one lump sum, right? And so if you've taken out a loan, unless it's something that you're doing for a close friend or a family member and it's not that big, right? Usually the way that you pay back a loan is through a series of uniform payments. Okay. Okay. Right. And so a lot of times, when you take out a loan from a bank, right? So you take like a mortgage out, and so you pay for a house or maybe pay for a car, right? You pay back that loan in kind of equal monthly installments, right? And so you pay a certain amount to the bank, each, or maybe a certain amount to the car dealership each month, and that amount is the same over a month of time until you've paid back the loan. Okay. And so this is also common in engineering as well. Okay. And so the symbol that we give for this series of annual payments is actually A. Okay. And so A might seem kind of a strange symbol for this, but the reason we call it A is because this usually represents an annual, an annual cash payment or an annual cash amount that takes place each year. Okay. And we saw a lot of these in our cash flow diagrams too, right? So when we were talking about things like maintenance payments, right, or maintenance costs, or salary for paying your staff, right? Those are costs that happen at a regular interval at the end of every time period, right? And so the way that we characterize that is as a uniform series. Okay. Okay. All right. And so just like we have a formula to convert between P and F, right? We also would like a formula to convert A into either P or F. Okay. All right. And so any questions on this so far? Okay. All right. And so by developing these formulas and developing the formulas that convert between A and P and F, what we're doing is we're basically finding a way to compute the equivalent uniform series payment to either a present sum or a future sum. Okay. All right. So let's look at first at the formula that converts between F and A, right? Okay. And so the formula that converts between F and A is going to be F is equal to A, okay, multiplied by the quantity 1 plus I raised to the n minus 1 divided by I. Okay. And so with this, if we know the amount of money that we're paying at a regular interval, and so if we know A and we know the interest rate, we can determine how much that will be worth in the future. Okay. And so let's do an example to kind of illustrate this, okay? All right, so in this example, let's say that you know, a new married couple, they want to save for a down payment on a house, okay? Right, and so let's say that this couple, they make an initial payment of $5,000 into an account, okay? Okay. Okay. And then they do this, they make this first deposit today. Okay. And then let's say that each year after that, for the next 2 years, they're going to add $7,500 to the account. Okay. Okay. And so at the end of year 1, they're going to add $7,500. And at the end of year 2, they're going to add $7,500 to that as well. Okay. All right. And so let's say that this account has an annual interest rate of 8.3%. Okay. Okay. Right. And so what we want to find out is that given all this information, we want to find out how much money is in the account after 2 years. Okay. Okay. All right. And so there's quite a few things going on in this problem, and so you know we'll kind of break it down kind of step by step. Yeah, it's an 8.3. Yeah, 8.3 interest rate. All right. Any questions? Any questions on the problem setup? Okay. All right. And so let's go ahead and break this down. You know, over you know, first of all, find out what we're solving for, and what we're given. Okay. And then we're going to classify all of the cash flows that we're given. Okay. All right. And so what we're searching for is the you know, the amount of money that's going to be in the account after 2 years. Okay. And so if we kind of dissect that phrase, we can say that, you know, how much money is in the account, and so we can say that that's kind of a one lump sum of money. Okay. And the fact that, you know, we want to find this out after 2 years tells us that, you know, we want to solve for a future sum. Okay. And so what this tells us is that, you know, all the other cash flows in the problem, we want to convert that to F. Okay. Okay. All right, and so let's take each of the cash flows that they gave us in the problem, and then let's convert that to a future sum. Okay. Right, and so first thing the problem tells us that they first make an initial deposit of $5,000. Okay. Okay. And so since this is an initial deposit that they're making today, you know, this is a present sum of money, right? So this is $5,000 that they have today that they're going to put into an account with an interest rate. Okay. And so to convert this into a future sum, we can just use our compound interest formula, right? And so we just say that F, or the future worth of this $5,000 is going to be that $5,000 times 1 plus 0.083, okay, raised to the second power, because, you know, we're only doing this for 2 years, okay? Right, and so if we perform the calculations, what we get is $5,864.45, okay? And so that initial deposit after 2 years, they're going to gain, or that $5,000 is equivalent to $5,864.45 2 years into the future, okay? And so the next cash flow that the problem tells us about is that the couple is going to deposit $7,500 each year, okay, into the account, right? And so since this is a uniform payment or a uniform series payment, right? They're making the same amount of money, or they're paying the same amount in each year, okay? We can classify this as an A, right? And so if we use our formula from before, okay, we convert F from A, we can say that F is equal to A times 1 plus I raised to the n, okay, minus 1 divided by I. Right. And so we have everything on the right hand side. Like, we know that A is $7,500. We know the interest rate. We know the number of periods. We know how to punch 1 into our calculator, right? And so if we do all those things, we end up with a future worth of $15,622.50. Okay. All right. And so now that we've converted both the initial deposit as well as the uniform payments into a future sum, we can go ahead and just add these together, and that's going to tell us the total amount of money in the account. Okay. Okay. And so the total F is going to be $5,864.45 plus $15,622.50. Okay. And so if you add these together, what you get is $21,486.95. Okay. Okay. Any questions? Any questions on this example here? Okay. All right. All right, and so just like we've done with the compound interest formula, you can manipulate you know, this current formula in order to solve for A, right? And so right now we have a formula here that solves for F given A, right? But we can also just, you know, manipulate this so that we solve for A given F. Okay. And so all we have to do is we just multiply by the by that you know, that factor with all the interest rates. Okay, as we said, that A is equal to F times I divided by 1 plus I to the n, okay, minus 1. Okay. Right, and so given an amount of money that you want to have in the future, right, you can compute how much money that you have to put away each during each period. Okay, and so this formula is actually really useful if you're budgeting for a very large purchase, right? And so let's say that you're saving up to buy a house, or maybe you're saving up to buy a car, right? And you need to make a minimum, you need to make a threshold for the down payment on such a purpose, right? And so this will be useful in telling you how much money that you need to save each month in order to make that future purchase. Okay. All right. We can also use this formula and then to also convert between P and A, right? Because right now we have a conversion between F and A, right? But we also want to convert between P and A as well, right? Right. And so to do that, the only thing we have to do is to just plug in for F, right? Because we already have a formula that relates F and P, right? So we already know that F is equal to P 1 plus I to the n power, okay? And so if we plug that in for that, then we automatically get a formula between A and P, okay? Right, and the result of that formula is A is equal to P times I times 1 plus I to the n divided by 1 plus I to the n minus 1. Okay. All right. Right. And so this formula right here, this is really useful. You can use this formula to determine how much money that you would pay each month to pay back a loan. Okay. Okay. And so if you take out a certain amount of money for a loan, right? So that's money that you have today. And so that's a present sum. And if you're going to pay that amount back in equal monthly payments, you can determine that amount by using this formula here, right? And so all you have to do is just plug in for P, the amount of money for the loan, and then plug in the interest rate and the amount of time, right? And that'll tell you how much you need to pay each month or each year, okay? And so if you're buying a new house, you just have to plug in, the amount of money that you paid for the house, you plug in the interest rate, you plug in the amount of time, and this will tell you what your monthly payment is going to be, okay? All right. And so finally, you can also manipulate this formula to give you a formula that converts between P and A, right? And so we're just going to take this guy and just move it over to the other side, right? And so before we leave today, let me show you that formula, okay? And so we can say that P is equal to A times 1 plus I to the n minus 1, all divided by I times 1 plus I raised to the n. Okay. Right. And so this will tell you, if you have a uniform series of payments, right, how much that would be worth, in the present time. Okay. Accounting for interest rates. Okay, so any final questions on any of these formulas, or just about cash flows or interest in general? All right, the question is, do we have to remember all these formulas for the exam? So no. And so I mean, this class is a little bit unique because it's virtual, and so the exams will be open notes and open book, and so you can use that, of course. But normally, even for in-person exams, I give you a formula sheet, because I think memorizing formulas is kind of, it's not a good use of your time. And so, I think you should know how to use formulas, but memorizing them is not, I think, is not really useful information. Yeah. Page 9, yes, I can definitely do that.
Professor,
Yep.
I have a question that's unrelated to this class.
Yep.
So I have you for FDA, and
Yep.
I was wondering, would it be fine if we don't have to show up to the class? Or
Oh yeah. So we'll
Okay.
so I'm going to use the same Zoom link that I did last week, and so if you don't want to, if you don't feel comfortable coming to the class, you can do that too.
Okay.
Yeah, and so I want to be flexible, because I know it's kind of a challenging time, and so I want to be there in person, just because on the registrar it's in person, and I think it's a
Yeah.
little bit easier to help people in person with FBA. But if you have a reason to stay home, I think you should stay home, and then you can participate in the lecture through Zoom, like we have been doing. Yeah.
Okay. Sounds good. Thank you.
Yep. All right. Yeah. So that's all I had planned for today. And so thank you guys for coming. And so this should hopefully help you get started a little bit on the homework. And then we'll finish this up on Thursday. So have a great afternoon, guys, and I'll see you guys on Thursday.
Thank you, Professor.
Thank you,
Take care.
Professor.
Thanks, guys.
Thank you.
Professor,
Yep.
just a
what's
quick
up?
question.
Mhm.
Will there be, because you already showed us the first cash flow, will there be other kind of cash flow kind of diagrams?
Yes. And so we're I think starting next week, we're going to combine basically cash flow diagrams and these guys. So
Right.
So right now I'm kind of, these are, I call these kind of the basic cash flows. And so we have present sums, we have future sums, we have uniform series, and we're going
Right.
to go over one more on Thursday, which is gradients. And then after that, I'm going to start throwing problems to you guys, which have kind of a bunch of these going on at the same time. So the cash flow diagram will then kind of become a tool for you to organize kind of just everything that's going on. Because if you're just reading the text for the problems, it can be a little bit hard to keep track of. But if you put them all into a cash flow diagram, it kind of makes it easy to see, which cash flows are going where, and how can you convert between one form and another. Yeah.
Right. Okay. Thank you.
Yep. Yeah, it won't be everything, because I think in the homework I asked you to do some problems with the arithmetic gradient, and so we're going to go over arithmetic gradient on Thursday. But this should be able to get you through, at least a big parts of problem 3 and 4. Yeah. All right. Did you guys have any other questions?
I have a question in the chat.
Oh, yeah. So so for the homework, so you should be able to finish most of it, except for the parts that say arithmetic gradient. And so anything that says arithmetic gradient, we're going to go over that on Thursday. Yep. Janelle, did you have any other questions? Are you away from keyboard, AFK? Okay, I'm gonna close the call then. So I'll see you on Thursday.